Have you ever looked up at the night sky and felt completely insignificant? Those tiny pinpricks of light aren't just stars, they're entire galaxies, each one a swirling metropolis of billions of suns, planets, and mysteries we're only beginning to unravel. The universe doesn't just hide its secrets, it flaunts them in plain sight, waiting for us to piece together the puzzle and what we've discovered so far. It's stranger, more breathtaking, and more unbelievable than anything science fiction could dream up. Take a single galaxy like our Milky Way, a colossal spiral spinning through space for over 13.6 billion years. Now imagine this, there are at least 2 trillion more galaxies out there, each with its own quirks, its own violent histories, and its own mind-bending phenomena. Some devour their neighbors, others spit out stars like fireworks, and some shouldn't even exist according to everything we thought we knew about physics. The deeper we look, the more the universe laughs at our rules. That's where this journey begins. Today, we're diving headfirst into the cosmic unknown with 30 facts about galaxies that will warp your sense of reality. We're talking about black holes with the mass of 40 billion suns, galaxies made almost entirely of dark matter, and celestial collisions so epic they bend spacetime itself. This isn't just trivia, it's a front-row ticket to the greatest show the cosmos has to offer. So buckle up, by the time we're done, you'll never look at the night sky the same way again. Here's something that will make your brain ache. Galaxies, those dazzling cities of stars, are almost entirely empty. That's right. If you could shrink the entire Milky Way down to the size of a football stadium, all its stars, planets, and cosmic debris would amount to nothing more than a handful of sand scattered across the field. The rest pure, unfilled void. We're talking about 99.9% nothingness. It sounds impossible when you gaze at a galaxy's glowing arms crammed with millions of stars. But those stars are so unimaginably far apart that collisions between them are rarer than winning the lottery 10 times in a row. Take our closest stellar neighbor, Proxima Centauri. It's over 4 light-years away. If the sun were the size of a grape in New York City, Proxima would be another grape sitting in Los Angeles. That's the mind-bending scale of empty we're dealing with. This cosmic ghost town flips everything we assume about density on its head. Even inside galaxies, matter is spread so thin that if you flew a spaceship through one, you'd likely go millions of years without hitting anything substantial. It's not just about distance either. The forces at play, gravity's delicate dance, the push and pull of dark matter, keep everything in place without needing to be packed together. So next time you look up at the Milky Way's glowing band, remember, you're staring at the universe's greatest illusion, a crowded sky that's really a breathtaking expanse of nothing. At the heart of our galaxy, lurking silently in the darkness, lies a monster so immense it defies comprehension, Sagittarius, a star. This supermassive black hole weighs in at a staggering 4 million times the mass of our Sun, yet it fits within a space no larger than Mercury's orbit. Think about that for a second, an object so dense, so powerful, it warps the very fabric of reality around it, bending light and time like a cosmic funhouse mirror. And here's the wildest part, it's not some distant spectacle. It's right there, 26,000 light-years away, pulling the strings of our entire galaxy like an invisible puppeteer. Watch the stars near Sagittarius, a star, and you'll see them performing a frantic, high-speed dance. Some whip around it at thousands of miles per second, their orbits stretched into chaotic ellipses by the black hole's relentless grip. Others spiral inward, doomed to be shredded into glowing streams of plasma in a process so violent it unleashes bursts of X-rays visible across the universe. And then there's the gas, enormous clouds of it swirling into the abyss, heating up to millions of degrees as they vanish beyond the point of no return. But how do we know any of this? Because humanity did the impossible. We took a picture of the invisible. In 2019, the Event Horizon Telescope, a global network of observatories working in unison, captured the first ever image of a black hole's shadow. That iconic orange ring, that's the edge of oblivion itself, the point where light can no longer escape. And while that image was of another black hole, the same technology has since turned its gaze toward Sagittarius, a star, peeling back the curtain on the dark heart of our own galactic home. What's truly mind-bending is how quiet this monster is. Despite its unimaginable power, Sagittarius, a star, is a lazy giant, barely feeding compared to the ravenous black holes in other galaxies. But don't mistake its calm for harmlessness. If even a single dense gas cloud wandered too close, it could awaken a feeding frenzy so bright it would outshine every star in the Milky Way combined. For now, it slumbers, but in the cosmic scale of time, for now could mean tomorrow or 1,000,000 years from now. One thing's certain, we're living in the shadow of a sleeping giant, and its presence shapes everything we see in the night sky. Picture this: two colossal cities of stars, each hundreds of thousands of light years across, hurtling toward one another at 250,000 miles per hour. It sounds like a recipe for cosmic catastrophe, but the impending collision between our Milky Way and the Andromeda Galaxy is anything but destructive. In fact, when these two galactic giants meet 4 billion years from now, they'll perform a graceful, almost ghostly dance, merging into something entirely new. Here's why it's so surreal. Despite containing over 1 trillion stars combined, galaxies are so mind-bogglingly vast that actual stellar collisions will be vanishingly rare. Think of it like two swarms of bees flying through each other. The individual bees rarely touch. The average distance between stars in a galaxy is so enormous that even during a head-on collision, solar systems glide past one another unscathed. Planets keep orbiting, stars keep burning, and life, if it exists out there, might not even notice the galactic reshuffling happening around them. But don't mistake this for a gentle process. Gravity will turn this merger into a spectacular show. As Andromeda's spiral arms first brush against the Milky Way, tidal forces will stretch both galaxies into surreal, ribbon-like structures. Stars will be flung into chaotic new orbits, some ejected into intergalactic space like cosmic outcasts. Over billions of years, the two galaxies will swing past each other multiple times, each pass distorting their shapes further until they finally settle into a single, football-shaped elliptical galaxy, dubbed Milkdromeda by astronomers. The night sky from Earth during this merger, absolutely unreal. As Andromeda approaches, it'll grow from a faint smudge to a brilliant, sprawling disk dominating the heavens. Then, as the galaxies intertwine, new star-forming regions will ignite like fireworks, painting the sky with glowing nebulae and young blue stars. Eventually, the familiar band of the Milky Way will vanish, replaced by a diffuse, golden haze as the merger completes. What's truly humbling is that this isn't some rare event. It's the universe's standard procedure. Galaxies grow by consuming neighbors, and we've caught countless others in the act. Look at the Antennae galaxies, two spirals currently mid-collision, their long tidal tails sparkling with newborn star clusters. Or NGC 772, a pair twisted into a celestial pretzel by gravity's relentless pull. Our cosmic fate is written in these celestial wreckages. The Milky Way itself has already swallowed smaller galaxies, and Andromeda's halo bears scars of past mergers. So while 4 billion years sounds impossibly distant, it's a reminder that the universe is anything but static. Galaxies breathe, evolve, and recycle themselves in an endless cycle. And when the final chapter of the Milky Way unfolds, it won't be an ending, just a spectacular transformation into something new. Staring back at us from the edge of time itself is GNZ11, ancient light from a galaxy born when the universe was just a cosmic toddler. This record-breaking relic, spotted a mere 400 million years after the Big Bang, shouldn't even be visible to our telescopes, yet there it is, a faint smudge of red in the darkness, a time capsule from an era so primordial that stars hadn't yet finished cooking the first heavy elements needed for planets or life. What makes GNZ 11 so astonishing isn't just its age, but its defiance of expectations. Here's a galaxy already fully formed, blazing with young stars, at a point when theorists believed the universe was still too hot and chaotic for such complexity. It's like finding a skyscraper in the middle of the Stone Age. The light we're seeing left GNZ 11 over 13.4 billion years ago, so long ago that the galaxy itself likely no longer exists in its original form. What we're witnessing is its ghost, a final message from an era when the first structures in the cosmos were just beginning to take shape. Scientists pinpointed GNZ 11 using the Hubble Space Telescope's deep field surveys, pushing its instruments to their absolute limits. The galaxy's light has been stretched into the infrared by the universe's expansion, a phenomenon called redshift so extreme that it borders on undetectable. Every photon we capture from it has traveled longer than the Earth has existed, surviving a journey through warping space-time and galactic collisions just to reach our lenses. But here's the real kicker. GNZ 11 isn't just old, it's inexplicably bright. Despite being 30 times smaller than the Milky Way, it pumps out newborn stars at a rate 20 times faster than our galaxy does today. This suggests the early universe might have been a far more dynamic, explosive place than we ever imagined, with galaxies forming in frenzied bursts rather than the slow, steady process we see today. The discovery forces us to rewrite cosmic history. If galaxies like GNZ 11 existed so soon after the Big Bang, it means the first star's population, Roman 3 stars, made purely of hydrogen and helium, must have ignited even earlier, perhaps within 200 million years of the universe's birth. These stellar pioneers, unimaginably massive and short-lived, would have died in titanic supernova, seeding space with the first heavy elements. GNZ 11 might be their descendant, a second-generation galaxy built from the ashes of those primordial giants. Telescopes like the James Webb Space Telescope are now hunting for even older galaxies, peering back to what astronomers call cosmic dawn. Every new discovery like GNZ 11 chips away at the mystery of how structure emerged from the Big Bang's aftermath. It's a reminder that the universe didn't wake up slowly. It burst onto the scene with a creativity and violence that still leaves us breathless. And somewhere out there, an even older galaxy waits to be found, ready to shatter our timelines once again. Some galaxies don't fade away, they just stop. Imagine a city where every factory shuts down overnight, every birth ceases, and silence replaces the hum of life. That's what astronomers call a red and dead galaxy, a cosmic graveyard where star formation ended billions of years ago, leaving behind only aging red giants slowly burning out like embers in a dying fire. These galactic relics shouldn't exist, yet they're everywhere, especially in dense galaxy clusters where they outnumber their star-forming cousins. The mystery isn't just why these galaxies died, it's how they died so quickly. Take Messier 87, that famous elliptical galaxy with the first photographed black hole. Its brightest stars are ancient, hinting that it hasn't birthed a major new star in over 7 billion years. At the same time the Earth was forming, M87 was already a fossil, the leading suspect, supermassive black holes with a deadly case of cosmic indigestion. Here's how it works. When a galaxy's central black hole feeds, it doesn't just swallow matter. It belches out energy in the form of jets and radiation so intense they can heat up a galaxy's gas reserves to millions of degrees. Star-forming gas needs to be cold and dense to collapse, so this superheated fuel becomes useless, stranding the galaxy without the raw materials to create new stars. It's like someone turning off the galaxy's oxygen supply. Some black holes go even further, blasting entire reservoirs of gas into intergalactic space with eruptions so powerful they're visible across the universe. But black holes aren't the only killers. In dense galaxy clusters, a process called ram pressure stripping can rip away a galaxy's gas as it plows through the hot plasma between galaxies. Picture a leaf blower aimed at a pile of dust, except here, the dust is an entire galaxy's future stars. The victims of this cosmic robbery, like the Sombrero Galaxy's stripped neighbors, are left with nothing but their aging stellar populations. The weirdest part, dead galaxies aren't always old. Some, like the bizarre red nuggets found in the early universe, shut down when the cosmos was just a few billion years old. These compact galaxies burned through their gas so fast that they flared up and died young, becoming celestial tombstones far sooner than expected. Others, like the zombie galaxies in the local universe, show flickers of rebirth when they steal gas from a neighbor, only to choke on it again when their black hole awakens. Why does this matter? Because these galactic corpses are time capsules. Their silent halos preserve clues about the universe's most violent eras, mergers, collisions, and black hole tantrums that shaped everything we see today. And if we're honest, they might also be the Milky Way's fate. One day, whether from black hole outbursts, gas exhaustion, or some unseen force, even our vibrant spiral could join the ranks of the red and dead. The universe doesn't just create, it retires, and in those retirement homes the stars still shine, they just don't dream anymore. The Milky Way has a secret. It's not the perfect flat spiral we see in textbooks. Instead, our galaxy twists and warps at its outer edges like a vinyl record left too long in the sun. Recent 3D maps of the galaxy reveal a startling S-shaped bend, with entire star clusters and gas clouds pulled upward on one side and downward on the other, creating a cosmic ripple stretching over 25,000 light-years. This galactic distortion isn't just artistic flair, it's a cosmic crime scene. The prime suspect, a dwarf galaxy called the Sagittarius Dwarf, a tiny neighbor that's been crashing through the Milky Way's outskirts like a bull in a china shop for billions of years. Each pass tugs on our galaxy's vast reservoir of dark matter, sending gravitational shockwaves through the stellar disk. Think of it like throwing a pebble into a pond, except the pebble is a galaxy 1/100th our size, and the ripples warp the fabric of the Milky Way itself. The warp isn't static either. It wobbles around the galactic center like a hula hoop, slowing down, gradually stabilizing before another collision sends it spiraling again. Astronomers have even detected younger stars being born along these warped edges, their trajectories forever skewed by the gravitational fallout. It's a reminder that galaxies aren't rigid sculptures. They're dynamic, ever-changing structures, bending under the weight of their own chaotic relationships. What's wildest is that we're living inside this warped disk without even noticing. From our vantage point near the Sun, the bend is invisible, hidden by the sheer scale of the galaxy. It took precise measurements of thousands of stars, particularly the pulsing beacons called Cepheid variables, to reveal the true shape of our cosmic home. Even now, the warp continues to evolve, a silent testament to the fact that in the universe, nothing stays perfectly flat for long. Galaxies aren't just random splatters of stars. They're cosmic snowflakes, each one sculpted by gravity into distinct shapes that tell the story of their lives. The universe has three main blueprints for these stellar metropolises: the elegant spirals, the featureless ellipticals, and the rebellious irregulars. Each type is a snapshot of a galaxy's past, present, and future, written in the language of swirling arms, glowing halos, and chaotic knots of light. Take the Whirlpool Galaxy, a textbook-perfect spiral. Its graceful arms, dusted with pink star-forming nebulae and young blue stars, spiral outward from a bright core like water circling a drain. These arms aren't static, they're density waves, cosmic traffic jams where gas compresses, triggering new star birth. The result, a vibrant, dynamic galaxy where creation never stops. Our own Milky Way is a spiral, though slightly more disorganized, with a central bar and frayed arms that hint at past collisions. Spiral galaxies are the universe's artists, constantly repainting themselves with fresh generations of stars. Then there's Messier 87, the titanic elliptical galaxy that gave us the first image of a black hole. Unlike spirals, ellipticals are smooth, featureless orbs. No arms, no gas, just a sea of ancient red stars swarming like bees around a hive. These galaxies are the universe's retirees, having long ago exhausted their star-making fuel. Some, like M87, grew massive by cannibalizing smaller neighbors, their gravity shredding incoming galaxies into stellar soup. Others might be the remnants of spiral galaxies that collided and merged, their delicate structures erased in the chaos. But the cosmos loves rule breakers, and irregular galaxies are the proof. These cosmic misfits, like the Large Magellanic Cloud orbiting the Milky Way, have no defined shape, just chaotic clumps of gas and young stars, as if the universe tossed them together haphazardly. Many are small, fragile things, their structures distorted by close encounters with larger galaxies. Others might be newborns, still figuring out their form. The most extreme, like the Galaxy NGC 516-9, are train wrecks mid-collision, their shapes torn apart by gravity's relentless tug-of-war. Shape isn't just about looks, it's a galactic fingerprint revealing age, history, and fate. Spirals rich with gas are stellar nurseries. Ellipticals drained of fuel are graveyards. Irregulars, they're the wild cards, proof that in the universe, beauty doesn't always mean symmetry. Next time you see a galaxy image, look closer. Its shape is a story, and it's begging to be read. Every galaxy in the universe has a secret skeleton, one we can't see but can't ignore. It's called dark matter, and without this invisible cosmic scaffolding, galaxies would fly apart like untied shoelaces in a hurricane. Here's the mind-bending truth: the stars, gas, and dust we admire in telescope images, they're just the decorative frosting. The real structure, 85% of a galaxy's mass, is made of something entirely invisible, a shadowy substance that neither emits nor reflects light. Yet its gravitational grip is the only thing preventing galaxies from spinning themselves into oblivion. The first clues emerged in the 1970s when astronomer Vera Rubin noticed something bizarre about galaxy rotation. According to Newton's laws, stars on the outer edges of a spiral galaxy should orbit slower than those near the center, just as Pluto trudges around the Sun more sluggishly than Mercury. But Rubin's measurements revealed the opposite: stars far from the galactic core were whipping around just as fast as their inner cousins. It was like watching the outer blades of a fan spin at the same speed as the ones near the motor, defying all logic. The only explanation, an enormous halo of unseen matter, must be enveloping each galaxy, its gravity propping up those reckless outer stars like an invisible hand. Modern observations paint an even stranger picture. Dark matter isn't just sprinkled randomly, it forms vast, intricate webs stretching across the universe, with galaxies clustering along their filaments like dew on a spider's web. We can map these hidden structures through gravitational lensing, where dark matter bends light from distant objects like a cosmic funhouse mirror. Some galaxies, like Dragonfly 44, take this to extremes. They're 99.99% dark matter, with barely any stars at all. These ghost galaxies are essentially chunks of pure shadow, floating through space with only a handful of stars as reluctant witnesses. The craziest part: after decades of searching, we still don't know what dark matter is. It doesn't collide with normal matter like atoms do. It passes through you right now as effortlessly as wind through a screen door. Theories range from as yet undiscovered particles to primordial black holes, but one thing's certain: galaxies as we know them couldn't exist without it. Every spiral arm, every star cluster, every planet orbits in the palm of an invisible giant. And until we solve this cosmic riddle, we're just scratching the surface of how galaxies truly work. The universe has a way of humbling us with sheer scale, and nothing does that better than IC 110, the largest known galaxy in existence. This cosmic colossus, lurking in the Virgo supercluster, stretches an incomprehensible 16 million light-years from edge to edge. To put that into perspective, if you replaced our Milky Way with IC 110, its outer boundaries would swallow the Andromeda Galaxy, the Triangulum Galaxy, and every satellite galaxy in our local group with room to spare. You could line up 50 Milky Ways across its diameter like beads on a string, and it still wouldn't fill the space. But size isn't even the most shocking thing about this galaxy. IC 110 belongs to a rare class called CD Galaxies, supergiant ellipticals found only at the hearts of dense galaxy clusters. These are the universe's ultimate galactic gluttons, grown fat by devouring countless smaller galaxies over billions of years. Imagine a celestial spider sitting at the center of a web, pulling in everything that drifts too close. That's IC 110's life story. Its diffuse halo contains trillions of stars, many stripped from victims during ancient collisions, now orbiting in chaotic swarms with no discernible structure. What's truly bizarre is how little we understand about galaxies this size. Theories suggest they form when multiple massive galaxies merge in quick succession, their black holes coalescing into a single, insatiable monster that heats up surrounding gas and shuts down star formation. The result is a ghostly leviathan, a galaxy so vast yet so dim that if you stood on a planet near its edge, the night sky would appear almost empty, its sparse stars spread too thin to create anything resembling a Milky Way-like band. Yet IC 110 isn't alone in its enormity. Alcyonius, a radio galaxy discovered in 2022, boasts lobes of plasma stretching 16 million light-years, a record holder in its own right. These galactic giants force us to rethink the upper limits of cosmic structure. Even black holes seem to play by different rules here. IC 110's central beast is estimated to weigh up to 100 billion solar masses, dwarfing Sagittarius, a star like a boulder beside a pebble. The irony, for all its immensity, IC 110 is fading. With no gas left to fuel new stars, it's destined to grow even darker and redder as its existing stars slowly burn out. Size, it seems, doesn't guarantee longevity in the cosmos, but while it lasts, this galactic Goliath stands as a reminder: the universe doesn't just build galaxies. Sometimes it builds monsters. Most stars live quiet, orderly lives orbiting their galaxies, but every now and then, the cosmos flings one into the void like a cosmic slingshot. These renegades, known as hypervelocity stars, hurtle through intergalactic space at speeds so extreme they escape their home galaxies entirely. Take HE 0437-5439, a massive blue star currently rocketing out of the Milky Way at 1.6 million miles per hour, fast enough to cross the distance from Earth to the Moon in just 14 minutes. At that speed, gravity's grip is no match for momentum, and this stellar fugitive is destined to wander the darkness between galaxies forever. How does a star reach such insane velocities? The leading theory points to our galaxy's central black hole, Sagittarius, a star. When a binary star system, two stars orbiting each other, wanders too close to this supermassive monster, chaos unfolds. The black hole's tidal forces can rip the pair apart, capturing one star while violently ejecting the other like a stone from a sling. The math is terrifyingly precise. As the doomed star swings around the black hole, it steals a fraction of the behemoth's rotational energy, converting it into raw speed. The result, a hypervelocity star catapulted outward at up to 2% the speed of light, carrying the fingerprint of Sagittarius, a star's hunger. But black holes aren't the only cosmic catapults. Galactic collisions like the eventual merger between the Milky Way and Andromeda can also launch stars into exile. As galaxies intertwine, their gravitational fields become chaotic playgrounds, scattering stars like billiard balls. Some gain so much kinetic energy during these encounters that they break free entirely, doomed to drift through the void as orphans of the cosmic dance. E0437-5439 is especially baffling because it shouldn't exist at all. By its speed and trajectory, astronomers estimate it was ejected around 100 million years ago, but its size and brightness suggest it's only 35 million years old. The contradiction, a star that young couldn't have traveled from the galactic center to its current position in that time. One wild theory proposes it was originally part of a trio, with two stars merging mid-ejection to create a younger, more massive object mid-flight. These stellar speedsters aren't just curiosities, they're cosmic breadcrumbs. By tracing their paths backward, we can map the Milky Way's gravitational field in 3D, uncovering hidden masses and dark matter distributions. Some hypervelocity stars might even carry planetary hitchhikers, rogue worlds torn from their orbits and sent careening into the abyss. Imagine the view from such a planet. As the home galaxy shrinks to a faint smudge, the traveler faces an eternity of uncharted darkness, a single point of light in an ocean of nothing. Yet for all their loneliness, hypervelocity stars are proof of the universe's unrelenting violence. Every galaxy, no matter how serene it appears, is a battlefield where gravity's whims can turn a star into a fugitive in the blink of a cosmic eye. And somewhere out there, new exiles are being born, silent witnesses to the chaos lurking behind the night sky's calm facade. Our universe has a habit of playing rough with galaxies, and nothing proves that better than the ones sporting not one, but two beating hearts at their core. Take Andromeda, our closest galactic neighbor, doesn't just have a single supermassive black hole anchoring its center. Peering through telescopes, astronomers spotted a second dense cluster of stars orbiting just 5 light-years away from the primary nucleus, locked in a slow gravitational waltz. This isn't some cosmic accident, it's the smoking gun of a violent merger billions of years ago, when Andromeda likely devoured a smaller galaxy and its core refused to fully assimilate. The physics behind these dual nuclei is as mesmerizing as it is destructive. When two galaxies collide, their central black holes initially sink toward the shared center due to friction with gas and stars, a process called dynamical friction. But here's where it gets weird. Once they get close enough, that friction weakens, leaving the black holes stranded in a precarious orbit around each other. In Andromeda's case, the secondary nucleus isn't just a naked black hole. It's a surviving fragment of the devoured galaxy's core, a dense knot of ancient stars that somehow resisted being torn apart during the collision. This stellar survivor now circles Andromeda's primary core like a ghostly echo of the feast. Watch this dance unfold over cosmic time, and the outcome gets even wilder. The two nuclei will gradually spiral closer, their orbits decaying as they fling stars away through gravitational slingshots, a phenomenon aptly called black hole scattering. In about 100 million years, Andromeda's twin cores will finally merge, unleashing gravitational waves so powerful they'll ripple across the fabric of space-time. Until then, this celestial oddball offers us a front-row seat to the messy aftermath of galactic cannibalism. Andromeda isn't alone in this peculiar condition. NGC 6670, a galaxy 400 million light-years away, boasts a pair of nuclei separated by a staggering 40,000 light-years, evidence of a recent collision still in progress. Meanwhile, Markarian 739 holds the record for the most unbalanced duo, one supermassive black hole weighing 60 million solar masses, accompanied by a second weighing just 1 million. Such mismatched pairs suggest galaxies don't always merge neatly. Sometimes, smaller cores survive like stubborn seeds in a cosmic blender. What does this mean for us? As the Milky Way hurtles toward its own merger with Andromeda, we're witnessing our future written in these dual nuclei. 4 billion years from now, Sagittarius, a star, and Andromeda's central black hole will begin their own deadly tango, potentially creating a new double nucleus of their own. For now, these galactic oddities stand as stark reminders. The universe doesn't build order without chaos, and every galaxy's center hides the scars of its violent past. Our galaxy isn't just a flat disk of stars. It's cocooned in a ghostly shroud of gas so hot it glows in X-rays, a seething halo of plasma stretching hundreds of thousands of light years into the void. This invisible furnace, discovered by space telescopes like Chandra, simmers at over 1 million degrees, wrapping the Milky Way in a faint, almost ethereal embrace. If you could see this halo with the naked eye, it would resemble a colossal, shimmering aurora, pulsing with the energy of countless atomic collisions, a reminder that even the emptiest corners of space are anything but tranquil. What's fueling this cosmic sauna? The leading theory points to ancient violent supernova explosions and galactic winds from the Milky Way's youth, which blasted gas outward so forcefully it never fell back. Picture the early galaxy as a tempestuous teenager, spewing material into space with the recklessness of a volcanic eruption. Over billions of years, that ejected gas cooled slightly but remained trapped in the galaxy's gravitational grip, forming a diffuse yet enormous reservoir. Now it floats around us like a forgotten exhalation, a fossilized breath from the Milky Way's most chaotic era. But here's where it gets even stranger. This halo isn't just a relic, it's a closed-loop recycling system. As intergalactic gas rains down onto the Milky Way, it collides with the halo's superheated material, creating shock waves that glow in X-rays. Some of this gas eventually cools enough to sink toward the disk, fueling new generations of stars. It's a cosmic water cycle, except instead of rain, we're talking about ionized oxygen and neon atoms dancing between states of extreme heat and relative calm. The halo's existence solves a galactic mystery. Where does all the missing matter go? For decades, astronomers struggled to account for all the normal matter, protons, neutrons, and electrons predicted by the Big Bang. Turns out, a significant chunk was hiding in plain sight, just too hot and diffused to see with optical telescopes. The halo's gas is so tenuous that a cubic meter of it might contain just a single atom, yet its sheer volume means it outweighs all the stars in the Milky Way combined. This discovery rewrites our understanding of galaxy evolution. Far from being static islands, galaxies are dynamic ecosystems, breathing in gas from the cosmos and exhaling it through stellar winds and explosions. Our Milky Way's halo isn't just a leftover. It's a living, churning boundary between our galactic home and the void beyond, a place where matter teeters on the edge of escape. And somewhere in its depths, atoms that once belonged to long-dead stars are preparing for their next act, waiting to be reborn in a future sun. Some galaxies don't fade gently into the cosmic night. They slam the door on star formation with brutal efficiency, transforming from stellar nurseries into celestial ghost towns in what astronomers call quenching. Picture a bustling factory where assembly lines suddenly freeze mid-production, leaving half-finished stars stranded in clouds of unused gas. This isn't a slow decline, it's a cosmic power outage, and the culprits range from ravenous black holes to intergalactic windstorms. Take the Sombrero Galaxy, a striking example of quenching in action. Its iconic dust lane and glowing bulge tell two conflicting stories, a past rich with furious star birth and a present where new stars are almost non-existent. The reason? Its supermassive black hole went through a phase of violent activity, flooding the galaxy with enough energy to heat surrounding gas to millions of degrees. Star-forming gas needs to be cold and dense to collapse, so this superheated fuel became useless, like trying to build snowmen in a sauna. Astronomers call this AGN feedback, where the active galactic nucleus, the black hole's energetic core, effectively pulls the plug on its own galaxy's future. But black holes aren't the only star formation assassins. In galaxy clusters, a process called RAM pressure stripping can act like a cosmic sandblaster. As galaxies plunge through the superheated plasma filling these clusters, The sheer force of the encounter rips away their gas reserves, the raw material for new stars. The result, galaxies like those in the Virgo cluster, left gas-poor and littered with the corpses of old red stars, their spiral arms fading into featureless hazes. Now flip the script to starburst galaxies like Messier 82, the Cigar Galaxy. Here, star formation isn't just active, it's explosive, with new stars igniting at rates hundreds of times faster than in the Milky Way. Galaxy collisions often trigger these frenzies as gravitational chaos compresses gas into dense knots where stars form en masse. The Cigar Galaxy's core is so littered with newborn stars that their combined radiation blows gas outward in colossal winds, a double-edged sword that might eventually quench the galaxy once fuel reserves are exhausted. What's fascinating is how quickly quenching can happen. Some galaxies transition from star-forming powerhouses to red and dead relics in as little as 100 million years, a blink on cosmic timescales. Others, like so-called Green Valley galaxies, are caught mid-quench, their star formation sputtering like an engine running out of fuel. These in-between systems offer clues to how galaxies meet their demise, whether through internal black hole outbursts or external forces like cluster environments. The lesson: galaxies don't just live and die, they can be murdered. Whether by the hand of their own black holes or the violence of their surroundings, their fate hinges on a fragile balance between creation and destruction. And somewhere out there, another galaxy is taking its last star-forming breath right now, its lights dimming as the universe quietly files it away among the fossils. Long before the universe built its majestic spirals and gargantuan ellipticals, it started small, painfully small. Among the faintest relics of this primordial era is Segway 2, a dwarf galaxy so tiny and dim it evaded detection until 29. This cosmic fossil weighs in at just 550,000 times the mass of our Sun, lighter than some globular clusters orbiting the Milky Way. Yet within its meager frame lies the chemical fingerprint of the cosmos's turbulent childhood, a time when galaxies were mere specks struggling to ignite their first stars. What makes these ancient dwarfs so special is how little they've changed. While massive galaxies like Andromeda have cannibalized neighbors and recycled gas for eons, Segway 2's stunted growth left it frozen in time. Its stars contain almost no heavy elements, just hydrogen, helium, and traces of lithium forged in the Big Bang itself. This pristine composition suggests it formed when the universe was less than 1 billion years old, from gas so untouched that its first stars burned without the pollution of later supernova debris. Spotting these galactic minnows is like finding a cave painting preserved under layers of volcanic ash, an unaltered snapshot of cosmic dawn. The scale of these early galaxies defies modern expectations. Current theories suggest the first star clusters could have been as petite as 10,000 solar masses, barely more than a hefty star cluster today. Gravity hadn't yet woven the cosmic web into its present-day filaments, leaving matter scattered in fragile clumps. Some, like the recently discovered Eridanus II, barely held onto their stars, their gravity so weak that passing galaxies could strip them bare with a gravitational sneeze. Yet against all odds, these galactic Lilliputians became the building blocks for everything we see today. Here's the twist: their small size made them cosmic overachievers. Without much gravity to trap heat, their gas cooled rapidly, allowing stars to form at breakneck efficiency. Some early dwarfs may have converted 90% of their gas into stars in just 100 million years, a pace that would leave modern galaxies gasping. The resulting supernova seeded space with the first heavy elements, enriching future generations of galaxies. Ironically, these galactic weaklings punched far above their weight, laying the groundwork for giants like our Milky Way. Yet for all their importance, these pioneers are vanishing. Surveys suggest 90% of predicted early dwarfs are missing, either too faint to detect or already devoured by larger galaxies. Each discovery, like Segway 2, is an archaeological treasure. hinting at the universe's scrappy beginnings. They remind us that today's glittering spiral disks and glowing ellipticals grew from the humblest origins, a cosmic rags to riches story written in starlight and dark matter. Galaxies usually follow predictable pattern spirals with flat disks, ellipticals with smooth blobs, but some cosmic rebels break all the rules by wearing their bling at impossible angles. Enter polar ring galaxies, celestial oddities like NGC 660, where a shimmering hoop of stars, gas, and dust orbits perpendicular to the main disk like a hula hoop around a flying saucer. This isn't just a quirk of perspective, it's the aftermath of a high-speed cosmic collision, a gravitational pirouette frozen in time. The mechanics behind these celestial acrobatics are as precise as they are violent. When two galaxies meet, the smaller one can get shredded into a ribbon of material, its stars scattered into a chaotic orbit around the larger galaxy's poles. Over millions of years, these scattered remains organized themselves into a crisp, stable ring, turning what was once a catastrophic crash into a breathtaking display of cosmic balance. NGC 660's ring spans over 40,000 light-years, a glittering belt of newborn stars and glowing hydrogen gas that shouldn't logically exist, yet there it spins, defying expectations. What makes these rings even wilder is their temporary nature. They're not permanent fixtures, just fleeting snapshots of galactic evolution. Over hundreds of millions of years, the ring's material will gradually wobble, warp, and eventually merge with the main disk, erasing all traces of the original collision. That's why spotting one today is like catching a figure skater mid-spin, a rare glimpse of an ephemeral pose in the universe's endless dance. Theories suggest polar rings might also be cosmic recycling plants. As gas in the ring cools, it funnels down toward the galaxy's center, igniting bursts of star formation where the streams intersect the disk. This creates bizarre, cross-shaped constellations impossible in ordinary galaxies, where star birth follows orderly spiral arms. Some polar rings even contain older stars than their host galaxies, hinting that the captured material might be fragments of an ancient victim, its identity erased but its legacy written in starlight. Beyond NGC 660, other polar ring galaxies push the envelope further. NGC 468, for instance, sports not one but two intersecting rings, a celestial double halo suggesting multiple collisions over its lifetime. Then there's the less common Hollywood galaxies, where the ring isn't polar but tilted at a dramatic 45-degree angle, as if caught mid-somersault. Each one is a forensic puzzle, its geometry revealing secrets about the violence that shaped it. These structures aren't just curiosities, they're stress testing our models of galactic dynamics. How do the rings stay stable without dispersing? Why do some galaxies retain them for billions of years while others dissolve them quickly? The answers could rewrite how we understand angular momentum in galaxies, proving once again that the universe's most flamboyant rule breakers often hold the keys to its deepest mysteries. So next time you see a picture of a neat spiral galaxy, remember somewhere out there, another one is wearing its chaos like a crown. The Milky Way isn't as unique as we might think. Floating 80 million light-years away in the constellation Pavo is its cosmic doppelganger, NGC 6744. This stunning spiral galaxy mirrors our own in almost every way. A similar size, the same graceful arms dusted with pink star-forming regions, and even a matching elongated central bar. If you placed images of the Milky Way and NGC 6744 side by side, you'd struggle to tell them apart. But this isn't just a celestial coincidence, it's a golden opportunity. By studying our galactic twin, we can glimpse the Milky Way from an outsider's perspective for the very first time. What makes NGC 6744 so special isn't just its resemblance, it's the details. Its spiral arms are a textbook example of density wave theory in action, with young blue stars tracing perfectly defined arcs like pearls on a cosmic necklace. The galaxy's outskirts even show signs of minor gravitational disturbances, likely caused by past encounters with smaller satellite galaxies, a mirror of our own galaxy's turbulent history with the Sagittarius dwarf. But here's the kicker. NGC 6744's star formation rate is slightly higher than the Milky Way's, giving us a front-row seat to how our galaxy might behave during more active phases of its life. Zoom in closer and the parallels get eerie. Both galaxies host supermassive black holes of comparable mass. NGC 6744's central beast weighs in at around 10 million suns, just a hair larger than Sagittarius, a star. Their surrounding nuclear star clusters also share uncanny similarities, with tightly packed ancient stars forming glowing halos around their respective black holes. Even their chemical compositions align, with matching abundances of elements like oxygen and iron, evidence that both galaxies have recycled their gas through generations of stars at nearly identical rates. But NGC 6744 isn't a perfect clone. One key difference: its disk appears slightly thicker than the Milky Way's, possibly due to a more violent merger history. Some astronomers speculate this extra thickness could be the result of a head-on collision with another galaxy billions of years ago, a fate our own galaxy might have narrowly avoided. Then there's the oddball companion galaxy, NGC 6744a, which orbits at a peculiar angle and shows signs of being slowly torn apart. Sound familiar? It's a haunting parallel to the Large Magellanic Cloud's dance with the Milky Way, though NGC 6744's satellite seems to be losing the gravitational tug of war far faster than our own. This galactic mirror holds profound implications because we're stuck inside the Milky Way. Key features, like the true shape of its spiral arms or the exact distribution of its dark matter, remain frustratingly elusive. NGC 6744 acts as a Rosetta Stone, allowing us to decode our own galaxy's hidden architecture. Recent studies even suggest it might possess a similar warp in its outer disk, reinforcing the idea that such distortions are common in large spirals. Every new observation peels back another layer of mystery, revealing not just how galaxies evolve, but how our own cosmic neighborhood might look to distant astronomers peering through their telescopes. The most poetic revelation: NGC 6744's light, the photons reaching our telescopes today, left its stars around the time the dinosaurs vanished from Earth. We're seeing our galactic twin as it existed in the deep past, while the Milky Way as we know it now won't be visible to observers in that galaxy for another 80 million years. It's a humbling reminder that in the grand tapestry of the universe, no galaxy is truly alone, just separated by time, distance, and the slow unfurling of cosmic history. Some of the universe's most massive galaxies are hiding in plain sight, not behind dust or distance, but because they barely glow at all. Take Dragonfly 44, a cosmic phantom lurking in the Coma cluster. This galaxy weighs about as much as the Milky Way, with a staggering 1 trillion times the mass of our Sun, yet emits less than 1% of our galaxy's light. If you could see it with the naked eye, it would appear as nothing more than a faint, diffuse smudge, like a ghostly fingerprint on black velvet. So how do we detect something so massive yet so dark? Gravitational lensing, nature's ultimate X-ray vision. When light from a background galaxy passes near Dragonfly 44, its immense gravity bends and distorts that light like a funhouse mirror. These warped images, called Einstein rings or arcs, reveal the unseen galaxy's mass and structure. It's like watching a couch cushion depress under the weight of an invisible person. You can't see the person, but the deformation gives them away. Dragonfly 44's lensing effects are so pronounced that they betray the presence of a dark matter halo stretching far beyond its sparse collection of visible stars. Here's where it gets eerie. Most of Dragonfly 44's stars orbit at dizzying speeds, whipping around the galaxy's core at over 300 kilometers per second, far too fast for the meager gravity its visible matter should produce. The only explanation, a gargantuan halo of dark matter, outweighing the galaxy's stars by a factor of 10,000. This makes Dragonfly 44 essentially a galaxy-sized clump of shadow, with just enough stars sprinkled in to hint at its existence. The discovery flips our understanding of galactic diversity on its head. These dark galaxies might be failed cosmic experiments, places where gas was too sparse or too hot to collapse into dense star-forming clouds. Others could be the stripped remnants of once normal galaxies, their gas torn away by encounters with larger neighbors, leaving only their dark matter skeletons behind. Some even speculate they're primordial dark matter clumps that never gathered enough normal matter to shine brightly. But Dragonfly 44 isn't alone. Ultra-diffuse galaxies like NGC 1052-DF2 take the concept further, with hardly any dark matter at all, a discovery that sent theorists scrambling. These contradictory finds suggest galaxies can winnow down to near invisibility through multiple paths, whether by being born dark or having their light slowly stolen. What's truly mind-bending is how many more might be out there. Current surveys could be missing thousands of these phantoms, their faint starlight lost in the glare of brighter neighbors or drowned in the glow of Earth's atmosphere. New telescopes like the Vera Rubin Observatory aim to hunt them using ultra-sensitive cameras capable of spotting the subtlest gravitational distortions. Every new find peels back another layer of the dark universe, proving that sometimes the cosmos hides its grandest structures not in shadow, but in near-perfect invisibility. Imagine a galaxy where darkness isn't just the void between stars, it's the very foundation holding everything together. Segway 1, a tiny satellite galaxy orbiting the Milky Way, is one such cosmic paradox. On the surface, it's unremarkable, just a few hundred ancient stars sprinkled across a patch of sky. But peer deeper and the truth emerges. Those stars are mere flecks of light in an ocean of shadow, outnumbered by dark matter a staggering 1,000 to 1. This isn't just a galaxy with some dark matter. It's a dark matter fortress wearing stars like decorative fairy lights. The numbers defy logic. Segway 1's visible stars account for less than 1% of its total mass. The rest, an invisible gravitational scaffold so dense that if you stood on a hypothetical planet within it, the night sky would feel eerily empty despite the titanic forces shaping your orbit. Stars here whip around at velocities that should send them flying into the void, yet something unseen holds them in place, like marionette strings tugging them through an invisible dance. The only explanation is a halo of dark matter so massive it distorts the very fabric of space around it. What's truly baffling is how galaxies like Segway 1 even form. Modern theories suggest they might be primordial relics, fragments of the universe's first dark matter clumps that failed to collect enough gas to birth stars in abundance. Picture the early cosmos as a churning sea of dark matter, with normal matter merely foam on its waves. In most places, gas pooled into these dark matter wells, igniting stars and building grand spirals. But in Segway 1's case, something went awry. Perhaps nearby radiation blasted away its gas, or maybe it formed in a cosmic desert where raw materials were scarce. The result, a galaxy-sized vault of shadow, its few stars acting as accidental witnesses to the unseen majority. Yet Segway 1 isn't alone. Triangulum 2 and Draco 2 exhibit similar dark matter dominance, their star-starved profiles challenging our notions of what a galaxy even is. These phantoms force astronomers to confront uncomfortable questions. Could the universe be teeming with nearly invisible dark matter galaxies, their presence betrayed only by subtle gravitational ripples? And if so, does this mean our current galaxy surveys, built on detecting light, are missing an entire shadow universe? The implications ripple through cosmology. If dark matter galaxies are common, they could solve the missing satellites problem. where far fewer dwarf galaxies orbit the Milky Way than simulations predict. Perhaps the missing galaxies aren't missing at all, just too dark to see. Even more tantalizing is the possibility that these starless dark matter clumps could be the perfect laboratories for detecting dark matter particles. With little gas or stars to create noise, any faint signals from particle collisions would stand out like whispers in a silent room. But the greatest lesson lies in humility. For centuries, we defined galaxies by their stars, only to discover that starlight might be the universe's afterthought, a decorative flourish on structures built from something we can't see or touch. Segue 1 and its kin remind us that the cosmos plays by rules we're only beginning to decipher, and the most profound truths often lurk just beyond the edge of visibility. Galaxies have a way of haunting themselves long after a star explodes in a cataclysmic supernova. Its light can continue to reverberate through space like a cosmic echo. One of the most stunning examples of this phenomenon unfolds in the Cigar Galaxy, where a supernova detonated in 2014, and its aftermath played out in slow motion across neighboring dust clouds. Time-lapse images reveal something extraordinary. Concentric rings of light expanding outward like ripples in a pond, each one marking where the explosion's flash illuminated different layers of interstellar dust. This isn't just reflected light, it's a celestial time machine showing us the same event over and over as photons bounce off cosmic debris at varying distances. The physics behind these light echoes is both simple and mind-bending. When a supernova erupts, its light races outward in all directions at, well, the speed of light. But if that light encounters a dense dust cloud light years away, some photons scatter toward us while others continue into the void. Because the dust lies at different distances, the scattered light arrives at Earth years or even decades later than the initial blast. The result, a single explosive event, appears to repeat itself across the sky, with each new ring revealing another hidden layer of the galaxy's dusty skeleton. In the Cigar Galaxy's case, the echo wasn't just poetic. It allowed astronomers to map the distribution of dust in 3 dimensions, turning an interstellar catastrophe into an impromptu CT scan of the cosmos. These echoes aren't just pretty visuals, they're forensic tools. By analyzing how the light dims and reddens as it passes through dust, scientists can decode the cloud's composition, how much carbon, silicates, or ice lurk in the darkness. Some echoes even reveal structures too faint to see directly, like delicate filaments of gas stretched thin by ancient stellar winds. In one remarkable case, a light echo from a 17th century supernova, observed but not understood at the time, was rediscovered in modern images, its ghostly rings finally explaining why long-dead astronomers recorded a new star that seemed to linger mysteriously in the sky. The most surreal aspect, we're essentially watching delayed broadcasts of cosmic violence. While the original star died centuries or millennia ago, its final moments are still playing out across the galaxy, bouncing between dust clouds like an intergenerational game of telephone. And somewhere out there, another supernova's light is currently mid-journey, its echoes already racing toward us but still years or centuries from reaching Earth. The universe doesn't just show us its history, it broadcasts it on loop if we know where to look. What's truly humbling is realizing that every glowing ring represents a choice of perspective. From another galaxy's viewpoint, those same dust clouds might reflect entirely different supernova, their echoes telling stories we'll never witness. The Cigar Galaxy's display is just one page in an infinite archive of cosmic afterimages, each one a fleeting testament to the fact that in space, even death isn't the end, just another signal looping through the void. The Milky Way didn't become the sprawling spiral we know today through peaceful growth. It's a cosmic predator built on a history of violent galactic feasts. 10 billion years ago, long before Earth formed, our galaxy collided with and devoured a smaller neighbor known as Gaia Enceladus, a dwarf galaxy roughly 1/4 its size. The evidence: stars orbiting in the Milky Way's halo at odd angles, their chemical signatures betraying them as cosmic refugees from another galaxy entirely. These ancient stellar survivors move against the galactic grain, their trajectories preserving the memory of a collision so violent it reshaped the Milky Way's very structure. This wasn't a quick merger, it was a drawn-out demolition. As Gaia Enceladus spiraled inward over hundreds of millions of years, tidal forces stretched it into stellar streams that wrapped around the young Milky Way like ribbons. Its core was torn apart, scattering stars across thousands of light years, while its dark matter blended seamlessly into our galaxy's halo. The merger injected so much energy into the Milky Way that its disk may have thickened, and some simulations suggest the collision even triggered a burst of star formation, igniting some of the oldest stars we see today. The aftermath left our galaxy forever changed, its growth fueled by the destruction of another. But the feasting didn't stop there. Right now, the Sagittarius Dwarf Elliptical Galaxy, a tiny satellite just 10,000 times the mass of the Milky Way, is being slowly torn apart in a death spiral. Astronomers have mapped its debris across the sky, tracing long, looping streams of stars that stretch entirely around our galaxy like a celestial serpent swallowing its own tail. Each pass strips away more of the dwarf stars, leaving behind ghostly trails that serve as breadcrumbs to its eventual doom, the most fascinating part. These mergers aren't just historical footnotes, they're actively shaping the Milky Way's future. The Sagittarius Dwarf's repeated plunges through our galactic plane are thought to be responsible for the Milky Way's warped edges, its gravitational punches sending ripples through the outer disk. Some theories even suggest these collisions may have triggered star formation in our own neighborhood, meaning the Sun, and by extension us, could owe its existence to these ancient galactic brawls. This cannibalistic history isn't unique. Look at Andromeda, and you'll see its halo littered with the remnants of devoured galaxies. Even our galactic neighbor, the Large Magellanic Cloud, shows signs of having absorbed smaller companions of its own. The lesson is clear: galaxies grow by consuming the weak, rewriting their own histories with each meal, and the Milky Way, it's still hungry. In 4 billion years, its most spectacular feast, yet the merger with Andromeda will begin. But until then, it's content with smaller snacks, a cosmic titan slowly picking at the bones of the universe. Galaxies aren't just islands of stars and gas, they're also colossal electromagnets, weaving invisible fields of force that stretch tens of thousands of light years across their spiral arms. The Milky Way's own magnetic field, though imperceptible to our eyes, is a labyrinth of cosmic energy, with lines of force so strong they can twist the paths of high-speed particles and sculpt entire clouds of star-forming gas. Picture the galaxy as a gigantic, spinning dynamo, where charged particles swirling through its disk generate magnetic fields like a cosmic-scale electric motor, except this motor has been running for over 13 billion years without an off switch. These fields aren't uniform, they're chaotic, tangled webs, stronger near the galaxy's core and weaker in the outer reaches, yet still powerful enough to leave fingerprints on everything they touch. When cosmic rays, high-energy particles from distant supernova, streak through the Milky Way, the magnetic field bends their trajectories into spirals, turning what would be a straight shot into a dizzying roller coaster ride. This bending isn't just a curiosity, it's a shield. Without these fields, Earth would be bombarded by far more radiation, making the galaxy a far less hospitable place for life as we know it. But magnetism's real magic happens in the nurseries of new stars. Dense clouds of gas, the raw material for stellar birth, are threaded with these invisible lines of force. As gravity pulls the gas inward to form stars, the magnetic fields resist, creating a tug-of-war that slows the process and determines how stars are born. In some cases, the fields channel gas into spinning disks around protostars, setting the stage for planetary systems like our own. In others, they eject material in powerful jets, launching newborn stars' excess energy back into space. The iconic pillars of creation in the Eagle Nebula, their delicate shapes are partly sculpted by magnetic pressures, invisible hands guiding the flow of cosmic dust. The Milky Way's field is so vast that it even leaves an imprint on the light passing through it, polarized starlight, where light waves vibrate in a preferred direction, reveals the field's orientation, allowing astronomers to map its structure like tracing the grain in cosmic wood. Recent observations show the field isn't just confined to the disk. It extends far into the halo, twisted into corkscrews by the galaxy's rotation, and possibly even connecting with the intergalactic magnetic web that threads the entire universe. What's astonishing is how delicate this system is. Magnetic fields in galaxies are 1,000,000 times weaker than a common fridge magnet, yet their cumulative effect shapes the evolution of entire galaxies. They regulate star formation, steer cosmic rays, and may even help funnel gas into supermassive black holes, fueling their growth. Without them, the Milky Way wouldn't just look different, it would behave differently, its spiral arms less defined, its star formation more erratic, its very structure unmoored from the forces that silently govern it. Yet for all their influence, these fields remain one of the least understood aspects of galactic anatomy. How did they first form? Are they primordial, dating back to the universe's infancy, or do they regenerate through some cosmic recycling process? Even now, instruments like the Square Kilometre Array are peeling back the layers of this mystery, listening to the faint radio whispers of electrons spiraling along magnetic field lines. Every new discovery hints that magnetism isn't just a side effect of galaxies, it's a cornerstone, as fundamental to their existence as gravity itself. So the next time you gaze at the Milky Way's glowing band, remember, you're not just seeing stars, you're witnessing the aftermath of an invisible force that's been shaping the cosmos since the beginning of time. At the bleeding edge of our cosmic horizon lies HD1, a galaxy so far away its light has traveled for 13.5 billion years to reach us, almost the entire age of the universe. Yet here's the twist. Due to the relentless expansion of space itself, HD1 isn't 13.5 billion light-years away today. It's a staggering 33 billion light-years distant, receding faster than its own light can chase us. This isn't a paradox, it's the universe playing a cosmic magic trick with spacetime, stretching the very fabric of reality while photons race through it. To unravel this, we need to distinguish between two mind-bending concepts, look-back time and proper distance. Look-back time is straightforward. It's how long the light has journeyed, a direct measure of how far into the past we're seeing. When we observe HD1, we're witnessing it as it existed just 300 million years after the Big Bang, a time when the first galaxies were still flickering to life in a murky, hydrogen-filled cosmos. But proper distance accounts for the universe's expansion during those 13.5 billion years. Think of it like running on a moving sidewalk. The light from HD1 started its marathon when the sidewalk was short, but by the time it reaches us, the sidewalk has stretched to 3 times its original length. What makes HD1 so extraordinary isn't just its distance, it's how absurdly bright it is for its age. This galaxy blazes with ultraviolet light, suggesting it's either birthing stars at a rate 100 times faster than the modern Milky Way, or harboring one of the earliest known supermassive black holes, voraciously devouring matter. Both scenarios defy expectations. In the early universe, gas hadn't yet clumped efficiently enough for such extreme star formation, and black holes shouldn't have had time to grow so massive. Yet HD1 laughs at these constraints, forcing us to reconsider how quickly cosmic structures could emerge from the primordial darkness. Discovering HD1 required pushing telescope technology to its limits. The galaxy's light is so redshifted, stretched by cosmic expansion into the infrared, that only observatories like the Subaru telescope and the James Webb Space Telescope can detect its faint whisper. Each photon we capture from it has survived a journey longer than Earth's entire existence, passing through countless galactic collisions and cosmic dawns just to imprint on our sensors. The implications ripple across cosmology. If HD1's brilliance stems from stars, it means galaxies started assembling sooner and faster than models predicted. If it's a black hole, we're staring at proof that these monsters could grow to billions of solar masses while the universe was still in diapers. Both possibilities rewrite the timeline of cosmic evolution, suggesting the early universe was a far more dynamic and explosive place than we ever imagined. And here's the haunting truth: HD1 likely no longer exists as we see it. The light reaching us today is its final message, a fossil from an era when the universe was just learning to build. By now, it's probably merged into a monstrous elliptical galaxy or been stripped bare by cosmic time. Yet its light lingers, a beacon from the edge of everything, reminding us that the universe's deepest secrets are written in the oldest light, if only we dare to look. Gravity doesn't just pull galaxies together. It choreographs them into breathtaking celestial ballets where entire star systems twist and stretch like cosmic taffy. The Mice galaxies, officially known as NGC 4676 and NGC 4676a, are one of the universe's most dazzling duets, locked in a gravitational waltz that stretched their spiral arms into two colossal tidal tails, each over 200,000 light-years long. These luminous streamers, studded with newborn star clusters and glowing gas, are the aftermath of a close encounter that began 300 million years ago when the galaxies first brushed past each other. Now they're caught in a slow-motion collision, their mutual gravity tugging stars and gas outward like strands of celestial spaghetti. Simulations reveal the intricate physics behind this dance. As the galaxies swung by one another, their gravity created tidal forces, a differential pull that stretches objects facing the attractor more than those farther away. Picture holding a rubber band between your hands and pulling. The middle stretches farthest. That's precisely what happened to these galaxies, their disks warping as stars and gas in the outer regions were yanked into those spectacular tails. Unlike a head-on collision where galaxies merge quickly, this glancing blow prolongs the spectacle, leaving the mica's cores still separate but forever changed by their gravitational flirtation. Zoom in closer and the chaos reveals surprising order. The tidal tails aren't random debris, they're cosmic conveyor belts, funneling gas into dense pockets where gravity ignites new stars. These tidal dwarf galaxies, forming along the tails, could survive as independent structures long after the parent galaxies finish merging. It's a galactic paradox, destruction breeding creation, as the violence of the interaction seeds fresh stellar nurseries in its wake. The mice aren't alone in this dance. The antennae galaxies showcase an even later stage, their twin nuclei spiraling toward an inevitable merger, while their tidal tails resembling insect antennae glow with the light of 1,000,000 newborn stars. Then there's NGC 6240, a rare triple galaxy interaction where three spirals are entangled in a gravitational knot, their tails intertwining like braided ribbon. Each of these systems acts as a time-lapse of galactic evolution, offering snapshots of a process that will one day befall the Milky Way and Andromeda. But here's the twist: these interactions aren't just beautiful, they're transformative. Galactic dances redistribute angular momentum, flinging stars into unusual orbits and funneling gas toward supermassive black holes, awakening them from dormancy. They also scramble a galaxy's shape, often turning elegant spirals into amorphous ellipticals. The mice, for instance, will eventually shed their tails, their cores merging into a single, featureless elliptical galaxy over the next billion years. Their dance, so graceful now, will end in a cosmic metamorphosis, proof that in the universe, even destruction can be a form of rebirth. What's humbling is realizing we're seeing these events in a single frame of a billion-year film. From another galaxy's perspective, the Milky Way and Andromeda might already look like the mice, their unseen tidal tails stretching across the void as they begin their own pass to dew. Gravity doesn't distinguish between grand spirals or tiny dwarfs. It weaves them all into the same intricate dance, a slow, inexorable ballet where every step leaves its mark on the cosmos. The Milky Way may look like a classic spiral galaxy in textbooks, but there's a twist. It's hiding a cosmic traffic jam at its heart. Instead of delicate arms swirling symmetrically around a round core, our galaxy sports a thick, elongated bar of stars spanning 27,000 light-years right through its center. Picture a giant stellar highway with millions of stars packed so tightly they form a rigid structure, all rotating together like a spinning pencil caught in a whirlpool. This galactic bar isn't just a curiosity, it's a powerhouse reshaping how stars are born across the entire Milky Way. How does a starry bar form in the first place? It starts with gravity's delicate dance. As spiral galaxies age, their inner regions naturally become more crowded, with stars orbiting at different speeds. Over time, these mismatched orbits can amplify tiny asymmetries, causing stars to pile up into an elongated shape rather than a perfect circle. Computer simulations show galactic bars emerging spontaneously, like waves suddenly standing up in a vibrating rope once a critical density of stars is reached. The Milky Way likely developed its bar between 8 and 10 billion years ago, long before our solar system even existed, as its central stars settled into this stable, rotating configuration. Now here's where things get dynamic. The bar isn't static, it's a cosmic mixing machine. As it rotates, its immense gravity creates shock waves in the surrounding gas, funneling vast amounts of hydrogen toward the galactic center like water swirling toward a drain. This forced migration has two explosive consequences. First, it feeds the supermassive black hole Sagittarius, a star, giving it sporadic feasts that trigger violent outbursts of energy. Second, and more crucially, it compresses gas clouds along the bar's leading edges, sparking furious waves of star formation. The regions where the bar meets the spiral arms, called orbital resonances, beckon stellar nurseries glowing with newborn stars. The iconic Orion Nebula, it might owe its existence to these very resonances where the bar's gravitational push concentrates star-forming fuel. But the bar's influence doesn't stop there. It also reshapes the Milky Way's spiral arms themselves. Unlike classic spiral galaxies with arms curling smoothly from the core, barred spirals like ours often have arms that seem to jump outward from the bar's tips, creating a distinct peanut-shaped distortion in the inner galaxy. This odd architecture means stars don't orbit the center in perfect circles. They're funneled into chaotic, rosette-shaped paths by the bar's relentless pull. Even our Sun, 26,000 light-years from the chaos, feels subtle tugs from this structure, causing it to oscillate slightly above and below the galactic plane as it orbits. The Milky Way isn't alone in this peculiarity. Over 2/3 of all spirals in the nearby universe show bars, suggesting they're a natural phase in galactic evolution. Some, like NGC 1300, exhibit bars so prominent they dominate the galaxy's entire appearance. Others, like the barred spiral NGC 778, showcase how bars can fade over time as gravitational interactions weaken them, hinting that our own galaxy's bar might one day dissolve, though not for billions of years. What's truly humbling is realizing we're inside this colossal structure, yet couldn't see its shape until modern telescopes mapped star motions in 3D. From our vantage point, the bar is invisible to the naked eye. Its stars blend seamlessly into the Milky Way's glowing band. Only by tracking the subtle back and forth motions of millions of stars could astronomers reconstruct its size and rotation, revealing we're living in a galaxy far more complex than the simple spiral we once imagined. So next time you gaze at the night sky, remember, you're not just looking at a flat disk of stars, you're witnessing a vast, spinning stellar engine, its hidden rhythms guiding the birth of stars and the fate of worlds. Most galaxies paint the cosmos in blues and reds, young stars blazing hot or old giants burning cool, but rare cosmic emeralds like J2240-0921 break the mold. This green bean galaxy glows with an eerie, uniform verdant hue, not from stars but from an electrified fog of oxygen lit up like a neon sign, the source of this otherworldly radiance. A quasar, a supermassive black hole's energy beam so intense it's ionizing gas across the entire galaxy, a process normally confined to tiny regions near the black hole itself. J2240's green halo spans 40,000 light-years, making it the universe's largest single fluorescent bulb, powered by the gravitational fury of a feeding singularity. What makes these green galaxies cosmic unicorns is their fleeting existence. The quasar phase responsible for their glow lasts maybe 10,000 years, a blink in galactic time. During this window, the black hole's radiation pressure has begun stripping away surrounding gas, but hasn't yet blown everything apart. The result is a delicate balance where ionized oxygen atoms emit that signature jade light as they relax back to lower energy states. Soon, by cosmic standards, the quasar will either exhaust its fuel or blast away the remaining gas, leaving the galaxy to fade into a more typical red as star formation shuts down. The discovery rewrote astrophysics playbooks. Before J2240, astronomers assumed such galaxy-wide ionization only occurred in quasars 100 times more powerful. This middle child quasar suggests even moderately active black holes can temporarily dye entire galaxies green under the right conditions. Stranger still, observations reveal the green glow isn't perfectly symmetrical. It forms intricate tendrils and bubbles, mapping where the quasar's energy punches through denser gas clouds like sunlight filtering through jungle leaves. These emerald galaxies also serve as cosmic Rosetta Stones. Their spectra reveal otherwise invisible structures, the distribution of intergalactic gas, the strength of the quasar's historical outbursts, even clues about how galaxies regulate black hole growth. Some show concentric rings of varying green intensity, evidence of the quasar flickering on and off over millennia like a cosmic strobe light. Others, like the smaller green P galaxies, demonstrate miniature versions of this phenomenon, where starbursts rather than quasars energize the gas. Yet for all their beauty, green galaxies are fundamentally tragic figures. Their brilliance marks the beginning of the end, the moment a galaxy's central black hole starts consuming itself into irrelevance. Within millions of years, J2240's glow will fade as its gas disperses, leaving behind a quenched galaxy where new stars can no longer form. The green phase is less about creation than destruction, a fleeting farewell performance before the cosmic lights dim for good, the most poetic detail. We're catching these galaxies at the perfect moment. Given the short duration of their green phase compared to the universe's age, spotting even one requires improbable luck, like stumbling upon a firefly's flash in a midnight forest. That we've found dozens suggests the cosmos is dotted with these ephemeral emeralds, each one a silent testament to black holes' power to paint the universe in colors no star could ever produce. Galaxies are supposed to follow rules. Dark matter provides the invisible scaffolding, stars decorate the visible structure, and gravity keeps everything in place. But the universe loves an exception, and NGC 1052-DF2 is a full-blown cosmic rebel. This ghostly galaxy, floating 65 million light-years away in the constellation Cetus, contains almost no dark matter whatsoever. Its stars move so sluggishly that if you applied standard physics, the galaxy should have torn itself apart eons ago. Yet here it is, a shimmering enigma that either breaks our understanding of dark matter or reveals just how little we truly know. The discovery sent shockwaves through astronomy because it shouldn't be possible. Dark matter isn't just a minor ingredient, it's the glue holding galaxies together. Without its gravitational pull, galaxies spin so fast they'd fling stars into the void like a runaway carousel. That's why finding NGC 1052-DF2 was like stumbling upon a skyscraper standing without a foundation. Initial observations showed its stars drifting at a leisurely pace, their motions betraying a total mass barely exceeding the visible stars. No hidden dark matter needed to explain their dance. Naturally, skepticism flared. Could measurement errors be to blame? The team behind the discovery anticipated this, cross-checking with multiple methods. They tracked the galaxy's globular clusters, dense groups of ancient stars, and found their speeds equally underwhelming. They mapped the galaxy's structure, ruling out hidden mass lurking in unseen corners. Even the galaxy's appearance hinted at its strangeness, an ultra-diffuse formation so sparse you could peer right through it like cosmic lace. Every test pointed to the same conclusion: this galaxy simply didn't play by dark matter's rules. Theories exploded like supernova. Maybe NGC 1052-DF2 was the victim of a galactic robbery, its dark matter stripped away by a violent encounter with a larger neighbor. Others proposed it formed unusually, birthed from gas expelled during a cosmic collision, leaving it star-rich but dark matter poor, the most radical suggestion. Dark matter might not be a single substance but multiple types, some of which could decouple from galaxies under rare conditions. Then came the plot twist. Astronomers found a second dark matter-deficient galaxy, NGC 1052-DF4, followed by several more. Suddenly, NGC 1052-DF2 wasn't just a fluke, it was part of a growing club of cosmic misfits. If these galaxies formed without dark matter, it challenges the very foundation of how we think structures emerge in the universe. The debate rages on, with some researchers still questioning the measurements while others see a hint of new physics lurking in the data. What's undeniable is that these oddballs force us to confront an uncomfortable truth: our models of galaxy formation might be missing a crucial chapter. Whether through exotic cosmic events or gaps in our understanding of dark matter itself, NGC 1052-DF2 and its kin are rewriting the rules one starry paradox at a time. Before galaxies perfected the art of star-making, the universe experimented with monsters. Picture a star so colossal it makes our sun look like a speck, a celestial titan 1,000 times more massive, burning at temperatures that defy physics as we know it. These hypothetical behemoths, dubbed population 3 stars, are thought to have illuminated the earliest galaxies, rewriting the cosmic rulebook with their brief, cataclysmic lives. Unlike modern stars, which contain traces of heavy elements, these primordial giants formed from pure hydrogen and helium, the only ingredients available after the Big Bang. Their absence today makes them ghostly legends, but their fingerprints linger everywhere, etched into the very atoms of our bodies. The physics of these stars bends the imagination. With no heavy elements to help radiate away heat, they likely contracted into denser, hotter cores than any star existing today. Theoretical models suggest they could have reached surface temperatures over 100,000 degrees, so blisteringly hot that most of their light poured out as ultraviolet radiation, ionizing the surrounding gas and carving bubbles in the cosmic darkness. Their sheer size meant they lived fast, burning through their nuclear fuel in just 2 or 3 million years before meeting spectacular ends. When these stars finally exploded, they didn't just die, they detonated with the energy of billions of supernovae packed into one event, a phenomenon called a pair instability supernova. These explosions weren't merely destructive, they were cosmic alchemy labs. For the first time in history, the universe forged elements heavier than helium: carbon, oxygen, silicon, and eventually iron. Every atom in your bones, every ring on your fingers, every breath of air you take originated in the hearts of these ancient giants or their explosive aftermaths. The first galaxies likely resembled toxic nurseries, their gas laced with the ashes of dead population 3 stars, enriching subsequent generations of smaller, longer-lived stars. This recycling process laid the groundwork for everything to come: planets, life, even the chemistry of interstellar space. The hunt for evidence of these stars is like searching for fossilized echoes. Astronomers scour the spectra of the most distant quasars, looking for traces of pristine gas untouched by stellar pollution, a sign that some pockets of the early universe might have missed the first waves of star formation. Others search for unusual supernova remnants in ancient galaxies, hoping to spot the chemical signatures of pair instability explosions. The James Webb Space Telescope has joined this quest, peering back to cosmic dawn with instruments sensitive enough to detect the infrared ghosts of these stars' final moments. What's haunting is realizing these stars might not be entirely extinct. Some theories suggest isolated population. 3 stars could still exist in the far reaches of dwarf galaxies, regions so untouched by cosmic evolution that they mimic conditions of the early universe. Others propose that under extremely rare circumstances, modern gas clouds might collapse into quasi-population 3 stars, though none have been found yet. Whether relics or entirely gone, their legacy is undeniable. These stellar pioneers didn't just light up the cosmos, they forged the very elements that made galaxies, planets, and us possible. Their absence today is a silent reminder that the universe was once a far more violent and creative place, a forge where the rules were still being written. Deep in the Milky Way's silent voids, hidden between the glow of stars, countless rogue planets drift like cosmic orphans, worlds without suns, untethered from any solar system. Astronomers estimate their numbers in the billions, far outnumbering the stars themselves. These lone wanderers didn't start life adrift. They were violently ejected from their birthplaces during the gravitational chaos of young star systems. Picture a planetary pinball machine, protoplanets slingshotting past gas giants or colliding with siblings, some flung into the abyss by the very forces that should have bound them. Detecting these invisible exiles requires ingenious cosmic detective work. Since rogue planets emit no light of their own, traditional telescopes are blind to them. Enter microlensing, a phenomenon where a planet's gravity bends and magnifies the light of a distant star passing behind it. Like a phantom briefly warping a spotlight, these unseen worlds betray their presence by distorting starlight in telltale ways. The effect lasts mere hours or days, a fleeting signature that requires constant sky monitoring to catch. Projects like OGLE and MOA have turned this method into an art, scanning millions of stars to capture these elusive events. Some of these rogue worlds might still cling to warmth from their violent births, failed stars like Jupiter-sized brown dwarfs glowing faintly with residual heat. Others, especially Earth-mass ice balls, could be frozen wastelands where temperatures hover near absolute zero. Yet even in their isolation, they might harbor secrets. Subsurface oceans kept liquid by tidal forces or radioactive decay could persist beneath icy crusts, making them dark, free-floating arcs for extremophile life. The scale of this phenomenon reshapes how we imagine galactic architecture. If rogue planets truly outnumber stars, they could form an invisible scaffolding throughout the Milky Way, their collective gravity subtly influencing the motion of visible matter. Some might even serve as unseen stepping stones for future interstellar travel. Cosmic pit stops in the vast emptiness between stars. Most haunting of all is the fate they represent. For every rogue planet we detect, countless more drift unseen, their trajectories carrying them through eternity without warmth or light. A few may eventually be captured by passing stars, gaining new orbits after eons of darkness. But most will wander forever, silent witnesses to the galaxy's turbulent, unrelenting nature, where even worlds can become nomads in the night. Markarian 1018 plays a cosmic game of peek-a-boo from 350 million light-years away. This otherwise unremarkable galaxy has done something extraordinary. It's changed its entire personality twice in just 30 years, flipping from dim to dazzling and back again like a malfunctioning light bulb. The culprit behind this celestial mood swing, a supermassive black hole with an eating disorder, cycling between gluttony and starvation in one of the most dramatic cases of AGN flickering ever observed. What we're witnessing isn't just random variation, it's the heartbeat of a galaxy's core, pulsing with the rhythm of matter spiraling toward oblivion. Here's how the cycle plays out. When gas and dust drift too close to the black hole, they don't fall straight in, they form a swirling accretion disk, heating up to millions of degrees and glowing brightly before crossing the event horizon. This is the active galactic nucleus phase, when the black hole transforms into a quasar, outshining all the galaxy's stars combined. But mark this, the AGN isn't a steady flame, it's a flickering torch, its brightness dictated by the chaotic flow of cosmic fuel. In Markarian 1018's case, something disrupted the buffet line. Maybe a star veered too close and was shredded, providing a sudden feast. Or perhaps clumps of gas collided in the disk, creating temporary bottlenecks. Whatever the cause, the black hole's meals became erratic, making the entire galaxy wax and wane in brightness over human timescales. The real surprise came when astronomers dug through old observations. Between 1980 and 2000, this galaxy dimmed by a factor of 10, then abruptly rebrightened by the same amount within just 5 years, a blink of an eye for galactic processes. That speed suggests something altered the accretion disk structure almost overnight. One theory points to instabilities in the magnetic fields threading the disk, which can abruptly choke off or unleash the flow of material. Another proposes that the disk occasionally puffs up like a soufflé, blocking our view of its hottest inner regions until it collapses back to normal. Markarian 1018 isn't alone in this cosmic strobe effect. NGC 1566, another AGN flickerer, dimmed so drastically in 2017 that astronomers initially thought their instruments had failed. These aren't malfunctioning telescopes, they're windows into black holes' messy eating habits. Unlike stellar black holes that swallow matter cleanly, supermassive ones at galactic centers are messy diners, spilling as much energy as they consume. When the food supply stutters, the whole system hiccups and the galaxy's core flickers in response. What makes this phenomenon so valuable is its human timescale. Most galactic processes unfold over billions of years, but AGN flickering lets us watch cosmic evolution in near real time. By monitoring these changes, we're essentially running a galactic lab experiment, testing how black holes regulate their own growth. The flickering might even explain why some quasars from the early universe switched off so abruptly. Their black holes didn't die, they just took a cosmic nap between meals. The lesson hidden in these fluctuations is humbling. We imagine black holes as insatiable monsters, but Markarian 1018 proves they're more like capricious toddlers prone to fits and bursts, gorging one moment and pushing the plate away the next. And when these giants at the heart of galaxies change their minds, the entire galaxy flickers in response, its brightness a mere side effect of a dark giant's digestion. Galaxies aren't scattered randomly across the cosmos, they're threaded along an invisible scaffold, a sprawling cosmic web of filaments that stretches across the observable universe like the veins of a colossal leaf. This vast structure, composed mostly of dark matter and ionized gas, connects galaxy clusters in delicate strands, forming a network so immense that the Milky Way is just one speck in a single thread. At the grandest scale, our galaxy belongs to the Laniakea supercluster, a mind-bending structure containing 100,000 galaxies across 500 million light-years, all bound together by the web's gravitational pull, flowing toward a mysterious region called the Great Attractor, like rivers drawn to a hidden sea. These filaments aren't theoretical. Simulations like the Millennium Run and Illustris TNG have brought the web to life, showing how dark matter's gravitational influence shaped the universe from its earliest moments. After the Big Bang, tiny quantum fluctuations grew under gravity's relentless pull, clumping dark matter into web-like structures where galaxies later formed at the densest intersections. The result, a cosmic blueprint where galaxies cluster along bright knots and stringy bridges, separated by vast, empty voids so barren they're called cosmic deserts. The largest filament discovered, the Hercules Corona Borealis Great Wall, spans 10 billion light-years, a staggering 1/10 the observable universe's diameter. What's wild is that we're inside this web, yet couldn't see it until recently. Mapping Laniakea required painstaking work. Astronomers tracked the motions of thousands of galaxies, noting how they all drift toward the same gravitational anchor. The visualization resembles a twirling galactic cyclone, with the Milky Way sitting on the outskirts like a suburb to this sprawling metropolis. At the web's nodes, galaxy clusters collide in violent mergers, while along the filaments, rivers of hydrogen gas flow fuel for future star formation. Even now, our local group of galaxies is sliding along a filament toward the Virgo cluster, riding the web's currents toward an eventual collision billions of years from now. The most humbling realization, this web is still growing. Dark energy stretches the voids, making filaments longer and thinner over time, while gravity keeps weaving new connections. Some threads will snap, leaving galaxy clusters isolated. Others will merge into thicker superhighways, and the Milky Way, it's just a passenger on this endless ride, caught in a celestial river whose destination we're only beginning to trace. The universe doesn't just contain galaxies, it's a living, breathing tapestry, and every star, every planet, every one of us is riding its threads into the unknown. From galaxies made almost entirely of invisible dark matter to black holes so massive they bend reality itself, the universe has shown us time and again that it plays by its own rules. Who would have imagined that our own Milky Way is warped like a vinyl record at the edges, or that galaxies can change their brightness in just a few years because of a black hole's messy eating habits? And let's not forget the rogue planets drifting through the void in numbers greater than the stars, proof that even worlds can become cosmic nomads. These discoveries don't just expand our knowledge, they shatter our expectations. The idea that galaxies are mostly empty, yet bound together by unseen forces, or that some are hurtling through space fast enough to escape their homes entirely, challenges everything we think we know about structure and stability in the cosmos. Even time itself bends to the universe's whims. Light from the earliest galaxies stretches and distorts as it races across an expanding cosmos, making the distant past visible in ways we never imagined possible. So which fact left you breathless? Was it the supermassive black holes lurking at the center of nearly every galaxy, or the ancient relics like Segway 1, where darkness outweighs starlight 1,000 to 1? Maybe it was the cosmic collisions, galaxies merging so violently they twist into surreal shapes, yet so gently that their stars rarely touch. Whatever it was, these mysteries remind us that the universe is far stranger, grander, and more unpredictable than we could ever conceive. The best part, this is just the beginning. Every discovery peels back another layer, revealing new questions, new wonders, and new cosmic oddities waiting to be explored. So keep looking up, stay curious, and never stop asking what if. If you love diving into the unknown, hit that subscribe button because the cosmos has endless surprises in store and we're just getting started. The universe isn't just out there, it's unfolding before our eyes, and the next mind-bending revelation could be just one observation away.